So now, if we're going to be completely accurate in our description of functions, we also have to consider the kind of functions that have endpoints. And we have to consider when is a function continuous at an endpoint. So here's our definition. A function is said to be continuous on a closed interval from a to b if the following conditions are satisfied. Number one, that the function is continuous at every interior point. You'll notice that we have round brackets. This is an interval. Round brackets are on a and b. So every point interior to a and b, not including the endpoints, are continuous. If that's the case, so far so good. We also want to talk about the function being continuous from the right at x equals a, and f of x being continuous from the left at x equals b. How do we know the difference? Well, in this particular case, you'll notice that we have a left-hand endpoint, and the only way to approach a left-hand endpoint is from the right, right? So in this particular case, we would want to ensure that f at a left-hand endpoint, that the value of the function equals the value of the limit as x approaches from the right of that point x equals a. So this function right over here visually is not continuous because it fails condition 2, right? It's not continuous from the right. Now, if we want to evaluate a right-hand endpoint, the only way to approach a right-hand endpoint is from the left. So in this case, we look at point B and we say, well, is the function continuous as x approaches b from the left? If it is continuous, that is, if we look at the value of the function at x equals b and the limit as x approaches b from the left, then we would say it is continuous. In this second case, it's not continuous because the two different values do not agree, but in this last graph, it does. Remember, when we're talking about continuity right here, we want to ensure that all three conditions are met, that the value of the function is defined, that the limit as we approach from either the left as appropriate exists, and that the two values agree with each other. So let's consider a specific example. Let's talk about this function. F of x equals the square root of x minus 1 whenever x is greater than 1, and it's equal to some value, we're not going to specify what value, at x equals 1. So f of x is equal to 1. So what would we do? Well, if we're looking for continuity, we say that, first of all, what is the value at x equals 1? Well, f of 1 is equal to whatever the value of a is. Right? So if I were to go over here to my graph and I were to find a somewhere along my y-axis, that would be the value that I assign to x equals 1 in this function. Now, the second thing we'd want to know is the limit as x approaches 1, but we can only approach 1 from the right. So we use a right-hand limit. We say the limit as x approaches 1 from the right of f of x, and we ask, does that exist? Well, in this case, yeah. If we take our limit as x approaches 1 from the right of the square root of x minus 1, this is the kind of function where it is behaved at least to the right of 1, so we can substitute in values of 1 that approach 1 from slightly greater, and we find that that approaches 0. So if we want continuity, we have to assure ourselves that the limit as x approaches 1 from the right of f of x is exactly equal to the value of the function at 1. Therefore, in order to make this function continuous, we have to say that the limit from the right, which was 0, is equal to a, and therefore this is only continuous if a is 0. Otherwise, it's not, right? So if we're looking at our value of a right over here, we'd have to make sure that our dot that defines it is, in fact, right in the place where we think it should be.